The next speaker is Hans-Peter de Koning, one of the fathers of SysML v2, and also, one of the great leaders over, over 4 decades of work within the European and international model-based systems engineering community. So he worked at European Space Agency as a thermal engineer, as a systems engineer, and on many missions, and and led the way to this point where we are now today. And it's a pleasure to have Hans-Peter here join us from Vilnius and speak to us all about the SysML v2 textual notation capabilities.
Thanks. Thanks, Greg. I'm not sharing, am I? Ooh, where is it? Oh, I am. Okay, great. Okay, so yeah, since this is a System as Code fest, I thought maybe we dive into the code because tomorrow we'll do with Tim. We do another more like an overview and really the more high-level stuff in SysML2. But today I want to highlight some of the capabilities. First of all, my background, like you also said, is I've been in mostly working in space industry in various engineering forms, but the last 10 years, before retirement in 2020, I was responsible for the work that Marcel is now doing, actually let's say shaping the MBSE introduction into current design and support to ESA projects, trying to leverage MBSE and get it inserted in, or let's say infused into the space business, space projects. Today I want to show a few things on, let's say, something that's close to my heart, so all the quantities, units, but especially also vectors and the more complicated stuff with quantities, and geometry. Because we look a lot at time, at let's say, time-based behavior, so the behavioral aspects. Structure is also important. So of course, we're not going to do a 3D cut tool into SysML, but we do need geometry in various forms. So early in the life cycle, we want to have a 3D configuration. We want basic information, so high level, let's say low fidelity geometry, but showing where things are, where sensors have fields of view, that should not be impeded by antennas or other stuff. And we want to be able to quickly visualize those kind of things so that the whole team with all the different disciplines that need to work together, they have a similar mental image and actually a practical image of where things are in 3D space. Also, we feel that, let's say, stay out areas or stay out volumes or mounting surfaces, enveloping volumes, fields of view that we already mentioned, but also human factors, so accessibility, if you have the human-machine interfaces. Everywhere, especially also in interface definition, and interface definition is one of the essential parts of systems engineering. They need to be precise on how things fit together, where things are relative to each other in 3D space. We want to be able to, if we do a robotic arm, we want to make sure that it doesn't move through something, some element of the system. Of course, we want to avoid collisions, etc. And then we have the geometry related to quantities like center of gravity, moments of inertia in space, in aeronautics. They're very, very important. And they're very important from the start. Is there a problem with the sound? Okay. I don't know where's my. Huh? Huh? Okay, I will do that. Yeah. Oh, sorry. Let me see where, am I sharing still or not? I'm sharing the wrong application, probably. So we're back. get rid of this one. Oh. Where's my... Okay, yep. Okay, so very quickly, so we have all these primitive shapes, so you can build geometry from basic building blocks, so the mathematical shapes. There's libraries that describe all these things. It's not very simple to use at the moment. There will be more simple language to do this. We have all these, well, basic descriptions with the attributes to describe the properties of those shapes. We have coordinate transformations, so many different kinds of sequences of rotations, translations, transformation matrices, all those kind of things that you need in order to place one shape with respect to another. And by default, we follow the compositional or the composite structures, let's say parts with nested parts. And a nested part is by default referencing the coordinate frame of the containing part in order to place it with respect to its parent, let's say. We also have, and this is important, we have similar to what we have in time with Allen's logic. So we have, let's say, really a semantic model that can be reasoned about. So in time, it's time ordering. In space, it's 3D region connection calculus. So this is a logic behind checking that, let's say, one solid touches another one, is enveloping the same volume, or is tangential touching, etc. So this is important because it allows later on reasoning in order to detect, let's say, collisions and interference between shapes. We also have constructive solid geometry, so you can build quite sophisticated shapes by, just like you do in a 3D CAD tool in the, let's say, the old style, by using the set operations to do intersections or unioning different volumes, etc. All of that is in SysML, built in. There's also a number of examples. I won't go into the details, but I'll show you a number of the ones. So one of the favorite ones is this very simplified quadcopter type model with here a field of view of the camera, just to show how it can be done. I'm working currently on an open source implementation with the API, driving it from FreeCAD. So FreeCAD is a quite nice and capable 3D CAD modeler that is representative of industrial CAD tools. And here's the corresponding SysML2 language. So typically, this kind of language would not be written, not authored manually, but it can be integrated with a sketching or 3D CAD-like tool and generate this kind of language directly from with an API. So this is currently done manually as a test case, but there are also already some implementations that can do this with software integration. So this is more there for reference. So now I want to go to an example with quantities and discretely sampled functions. So the basic model in SysML, so this is the underlying meta model with scalar quantity value is the, let's say, the top level type of any kind of quantity, and it's always referencing what we call a measurement unit or a scalar measurement reference in general, which supports all the different kinds of scales and units that you can have. Let me check. But we are extending this with vector and tensor quantity values. So there's a very elaborate ontology in order to rebase all of this on the same theory. So where a scalar quantity just has a single measurement reference, which is typically a unit, a vector quantity has a measurement reference that is basically capturing the vector space and a coordinatized vector space, so a coordinate frame that provides the reference for interpreting what a vector is in a vector space. And the same for tensors, which are higher order. So let's say a vector is an order 1 tensor. Tensors typically are order 2 or higher. And scalar are considered order 0 tensors. So we use these coordinate frames. A number of the coordinate frames are provided in the ISQ libraries, so they are available from the get-go. And if domains need more particular coordinate frames, they can be defined by extension, extending the standard libraries. So we have again the coordinate transformation. This is an overview of all the standard libraries there are. So all of the ISO 80000 quantities and units are there, including the vector quantities that are included inside them. And then we add a number of standard coordinate frames. So a number of examples are available in the SysML release that is available on GitHub. So that is part of the normal distribution that we try to update every month. And now I want to show one actual package that shows a number of these kind of concepts in code. So I'll switch to C-side. If that, where is it? So here, just to show how this works. So what I've done is to allow a very simplistic or very simple thing is a time series where I try to capture the trajectory of something going on a mission. So we need a time scale, we need a reference for time. So this is the way we define mission elapsed time. So mission elapsed time is just the accumulated time that elapsed since the start of a mission. So with the space mission, it's easy because 0 is really when you start the launch. So that is typically done as you take that as t equals 0. In this case, the unit is seconds, the definitional epoch, so this is the starting point of the time scale, has value 0, and we also can add the corresponding epoch in UTC. UTC is defined, so if I click on UTC, it just jumps to the standard definition of it. So if I go back, it is basically a 1D coordinate transformation on the time scale. So, yeah? Yeah, so I have 2 hands. That's easier. Okay, so it's a 1D coordinate transformation to shift, let's say, the definitional epoch onto the time scale. Another chair, yeah. So then we can define a mission elapsed time scale with a shorthand here, with a short name. We can also, for a particular mission, we can encode using the ISO 8601 encoding. So we just relate it to a precise timestamp, let's say on the microsecond with UTC. And we define a type that is mission elapsed time value. Then we can define a spatial coordinate frame, which is Cartesian, and we use the same notation as we use for the normal units, but now we have them for 3 axes. So this is just stating that each of the axes uses meter as the unit. And in addition, we can define a velocity frame And that's very nice. So we have this expression. So you can just divide the spatial frame by second, and you get meter per second velocity frame with the axes aligned with the space position, or the position vector frame, which is the 3D spatial frame. Similarly, for the acceleration, you can divide it by second again. So you divide the velocity frame by second, and you get meter per second square. So this allows a very powerful way to quickly define quite sophisticated vector spaces in which you can operate with vectors. So then in the trajectory example, we need a bit more. We need some structure to collect, let's say, position, velocity, and acceleration in one compound attribute. Then we need a trajectory sample. So this is one sample, so discrete sampling of one so all the values of position, velocity, and acceleration at one point in time. We define the trajectory as the collection of samples, which is basically specializing the standardized sample function. And then we can define a particular trajectory. So I'm just putting the first 3 points of the time series in this kind of notation. So here you see what this looks like. And you can also even use the linear interpolation function in order to later on calculate intermediate points or intermediate positions and velocities and accelerations by doing linear interpolation with respect to the time axis or the time series. So just to show, what kind of things are possible in relatively readable textual notation, and then I will try to close.
Yeah. So if I can make a joke, when it comes to geometry, visual notation is no help either. So yeah. So let's try to summarize
So this would be, let's say, a human readable view on exactly the same information. Huh? So it's exactly the same information, but now in an Excel type table, which is much easier to read, of course, but it's not readable by machine, and not in an unambiguous way, at least. So just to close, I'm going to continue with this stuff. Next meeting in San Francisco with the OMG and the systems modeling community, trying to do the full implementation of the bidirectional link with an actual geometry modeling tool. The nice thing is now we can use this also to do rigid body kinematics. So if you want to have a robot that's articulated with some control algorithm, we can easily parameterize the coordinate transformations and make them one or more variables, for instance, rotation angle about one of the axes of a let's say of a hinge in the in articulation in the robot arm and things like that. So there's a lot of interesting things we can do with this. I'll leave it at that.
Thanks so much, Hans-Peter. So it's really exciting to see, and there's clearly so much to explore. So it's all available online to everyone to try and see and play around with and see what can be made with SysML 2 and 3D geometry, and also in an S-code way.